I'm Max Desiatov, a software engineer on the Swift team at Apple. Today we'll talk about WebAssembly and why it is interesting in the context of Swift. We'll start with an introduction to WebAssembly and also have a look at the Swift package written and built for WebAssembly. We'll see it running in a server environment, but it can be easily extended and adapted for more platforms as needed. I'll wrap up with some pointers for where to go from here. WebAssembly support in Swift was developed by the open source community with the fork of the compiler previously hosted by the Swift Wasm organization on GitHub. Now, with all of the toolchain patches merged upstream earlier this year, recent nightly snapshots of Swift from swift.org gained experimental support for WebAssembly. Bringing Swift to new platforms is always exciting, but let's start with an obvious question. What is WebAssembly? It's a virtual instruction set initially designed for high-performance browser apps and standardized by World Wide Web Consortium in 2017. You'll frequently see it called Wasm, which is a contraction I'll use here from now on. You'd ask, what's the point of a virtual CPU? That's a ton of overhead, right? But as Wasm was designed with efficiency and security in mind, you can embed a Wasm module with low overhead as a plugin, which has no access to the outside world by default. It means that with care, you can use it for untrusted code execution. Thankfully, nothing in the Wasm specification ties it to the browser environment, so it is general enough to be portable to any platform. The smallest unit of distribution for Wasm is a module. A Wasm module instance is a module that's parsed into memory and has its internal state set up and ready for execution. An implementation of Wasm specification is called the runtime. It can instantiate one or more modules and execute them according to the spec. A runtime is usually embedded in an application that loads Wasm modules as plugins. And for passing data around, the runtime can import and export functions to and from the host app. If you consider adding plugin-like functionality to your app, you'll quickly come up with certain questions. For example, how would plugins communicate with the outside world? How can complex values be passed around between the plugin and the host app? And how can a host app prevent malicious plugins from breaching security? While most of you won't need to disassemble a Wasm module or write a Wasm runtime from scratch, knowing how it works at a lower level will help you answer these questions. Let's dive in to understand how Wasm is designed for security and efficiency from the ground up. If you're into compilers, you may see the resemblance between Wasm instruction set and an intermediate representation used by modern compilers, such as LVM. This means that Wasm is somewhere between the raw binary code used by real CPUs and high-level code you write in languages like Swift. This is what also makes Wasm portable. It's abstract enough not to encode the implementation details of end user's architecture it will be running on. And it's up to a runtime to either interpret or translate a Wasm binary to native machine code. Most of heavy optimizations were already made on this binary module before it reaches a Wasm runtime. Thanks to that, the runtime can focus on bridging this narrow gap between WebAssembly and real machine code. A typical workflow for a Swift developer targeting Wasm is to run the toolchain on their source code with Wasm selected as a target platform. With everything linked statically, you get a binary Wasm module as the build output. You can either use a standalone Wasm runtime executable or embed it as a library into a host app, as you saw earlier, to execute code contained in a Wasm module. How does that actually work? Under the hood, Wasm VM is a stack machine where instruction operands are pushed onto the stack before execution. These operands can be either numbers, integers and floats, or opaque references provided by the host environment. The virtual machine can also have access to a linear memory, which is a contiguous array of bytes pre-allocated by the host. A Wasm module can utilize it for dynamic allocations and other operations that don't fit on the stack. Later in the demo project, we'll have a look at a human-readable representation of Wasm, its text format, which is usually abbreviated as WAT. Files containing it also have a WAT extension. Before we proceed to the text format, it's helpful to visualize how WebAssembly modules are executed. A module is just an inert binary read from local storage or network, like an executable or a library for any other platform. To get it running, one needs to instantiate it in the memory space of the host with all of the required state prepared. And the closest analogy to that is a process spawned by an operating system before running. So how does that look in practice? A Wasm module instance at a given moment has multiple aspects of its state defined. Let's start with the stack at the bottom left. Wasm is a stack machine after all. I put 3 placeholder values there for illustration purposes, but of course it can contain arbitrary amount of values in theory, limited in practice by Wasm runtime. Only elements at the top can be used as instruction operands. Addressing items at the bottom or middle of the stack is not allowed. As for instructions, those are coming from the executed binary module. What's displayed here is just a sliding window of 3 instructions that can fit here for illustration purposes. Of course, a real module is not limited to just 3 instructions, and as we progress, you'll see new instructions coming in from the bottom as this window moves down. At the bottom right, there are locals, which are scoped to every function call, and globals, which are scoped to a module instance. Globals can also be exported and imported for sharing between different module instances. Logical question is why you need locals when you already work with items on the stack. As was said, the runtime is only allowed to pop items off the stack in the order they were pushed onto the stack, and only one stack is available globally. So even to swap 2 items at the top of the stack or duplicate a top item, you still need some temporary storage, which is what locals are providing. Additionally, function arguments are always passed as locals. So a Wasm function with 5 parameters will always have at least 5 locals for storing argument values. Lastly, at the top half of this slide, we see a linear memory instance, which is a region of readable and writable storage that can grow, into which instructions have arbitrary access. Again, yet another place for storing data. If your Wasm module needs random access to dynamically sized data, basically any heap allocations, and as you know in Swift, most of the data structures like arrays, strings, and dictionaries, especially the mutable ones, need dynamic allocations. You need some amount of linear memory to work on when it is compiled to Wasm. Stack can grow dynamically, but it doesn't allow random access via an address. While locals and globals are fixed and are known and their size and amount is known at compile time. As usual with the random access memory on any platform, it's just a soup of data at any given moment. Here we fill it with Unicode characters for example purposes. Important to know that linear memory can only be used for data. Instructions have their own completely separate internal address space. In Wasm, these instruction addresses are not even exposed or observed. There are no go-to or jump instructions, and only structured control flow is allowed. It is a nice security property, as with a well-behaved Wasm runtime, an author of a malicious module won't be able to assemble Wasm code on the fly in the linear memory of the same module and then to start executing it, which is one of the common attack factors on other platforms. Now let's finally see some action. The currently highlighted instruction i64 const1 at the top is ready for execution. This will put a constant 1 as a 64-bit integer at the top of the stack. Next instruction is local get 0, where locals has 0 index, so this will get a value of a local at index 0. Number 10 is a 64-bit integer. The number is highlighted at the top of the locals list, and the runtime is ready to execute this instruction. Great. Stack has grown again with number 10 at the top. Next instruction is i64 sub, which subtracts 2 64-bit integers at the top of the stack. You can see 2 operands highlighted at the top of the stack, and instruction is ready. Results of instructions that produce any values are put at the top of the stack again. So 10 minus 1 is, of course, 9. Now let's see how function calls work with more complex data. When calling functions, only primitive data like integers and floats can be passed as arguments. So how can you pass a string of arbitrary length? Naively, you could represent each character as a separate argument, maybe packing multiple ASCII characters in each 32-bit or 64-bit integer arguments. And this could work for short strings, but the most general approach is to pass an address in linear memory and the length of the string in bytes for the called function to read. Thus, the next instruction pushes 32-bit number 0 to the stack, which is an address in the linear memory. Here I wrote it in its hexadecimal form, which is commonly used for memory addresses. We can see the hello world string in linear memory starts at index 0. 0 is now pushed at the top of the stack, and the next instruction pushes the number of characters in hello world, which is 13 bytes, also a 32-bit integer. Both instruction operands are on the stack, and we're ready to execute the call print instruction. Usually under the hood, a print function would call a predefined import coming from the Wasm runtime. Let's assume that in this case, the import printed hello world to the console. Lastly, let's have a quick look at globals. Global set instruction will take a stack operand and write it to a global with a given index, 0 in this case. 64-bit integer is at the top of the stack, and the global was updated with that value. Now we can proceed to a more practical demonstration, a function written in Wasm text format, running in a Wasm runtime. I'll need to switch to mirroring. 1 second, please. Is that big enough? Let's have a look at the Wasm text format I mentioned earlier. You wouldn't write this by hand, but this is a representation of the final output of the compiler. If you disassemble a binary Wasm module, it will look similar to this. WebAssembly text format is a Lisp-like language, so anyone familiar with the Lisp programming language in the audience, raise your hands. Oh, great. But if you don't know Lisp, there's nothing to be afraid of. The gist is that Lisp has an incredibly simple syntax, which consists of nested lists delimited with parentheses. While Wasm text format is similar to Lisp syntactically, as I said, it is the semantics of it is closer to compiler intermediate representation. There are both low-level instructions, but also higher-level control flow concepts like if, then, else, branching, loops, and function calls, of course. Within a module that's introduced with the module keyword, you can see there are functions with their named parameters and the result types defined below. And control flow can be nested and contains blocks of expressions. To interoperate with the outside world, a Wasm module needs to declare exports and imports, which you can see in the top. In this example, the print function is imported from the host module, and the main function is exported for the host to use as an entry point. When it instantiates this module, it would call the main function. Below imports and exports, there is a linear memory declaration. Number 1 means a single memory page amounting to 64 kilobyte is allocated when the module is instantiated. Below that, a factorial function is declared with a single parameter and a single result, both of 64-bit integer type. As a reminder, a factorial of an integer n equals to the same integer multiplied by n minus 1, n minus 2, and so on until this decreasing sequence of factors reaches number 1. So factorial of 5 equals to 5 multiplied by 4, by 3, by 2, by 1. The body of the function is a classic recursive factorial implementation. The if expression with 64-bit integer as a result evaluates to 1 if the function argument equals to 0, which is what i64 EQZ instruction checks for. Otherwise, the function argument is multiplied by the result of the recursive call, and the function argument decremented by 1. Remember, we visualized these 3 instructions just a few minutes ago. The main function below calls factorial function with 64-bit integer 10 as an argument and calls the print function below that. At the bottom, the data directive populates linear memory at address 0 with a hello world string, which is then used by the print call above in the main function. Now remember, on slides you've seen a linear sequence of instructions executed one by one, modifying the stack. How does this nested code match that linear sequence? Turns out WebAssembly text format supports a linear form where instructions are listed in the order that they appear in the final binary. So in fact, there is a trivial algorithm that can transform from the nested list-like form into a flat linear form. Since nested instructions form a tree, you can use depth-first search in left-to-right direction and move each tree node above the currently processed instruction. Let's try that. Let's try to modify and transform this, the sequence of a few instructions manually. So the most deeply nested instruction here is local get. We paste it over here. Then I64 EQZ. We'll paste it over here as well. The next one, deeply nested, is I64 const. We then unwrap it over here and remove the print. Then let's compare it to the flat form, and we can see that pretty much the 4 instructions are the same. And essentially, the assembler can do this transformation manually. But it is useful to know, again, if you're looking at disassembly, you can stumble upon these 2 different forms that are equivalent to each other. The nested form is more human readable, but the flat form directly represents the final Wasm binary. So how do we run this code to see that it's all valid? I have a package prepared here that depends on WasmKit, which is a Wasm runtime available as a Swift package. And it can compile Wasm text format into binaries ready for execution. Here's how that works. We import both WasmKit modules. Just below that, we compute the path to our factorial demo wat file and compile that into a binary with wat to Wasm function below that. We parse the binary back to WasmKit intermediate representation and set up the runtime with the host module and the print function. Let me unwrap that. The string is then decoded from the memory slice of the module as UTF-8 and printed with the host's print function. We then return back an empty result from the guest module. At the bottom, we instantiate the module and call its main function. Let's run that to see the result. Great. We see that the guest module printed the hello world string. It passed the linear memory address and the byte count to the host. Then the host was able to read the linear memory with this information and get the slice that amounts to just that string. And below that, we see that the computed 64-bit integer value, which is a factorial of 10, returned from the main function. Let's also try to run the flat form and see whether it is equivalent to the nested form as well. Great. It's pretty much the same, exactly the same. Now back to slides. Coming back to the module state, let's put it into the larger context. A Wasm runtime can create a single module instance, and that's the simplest scenario. Multiple module instances can talk to each other via imported and exported functions and globals. Note that you can launch the same module multiple times as multiple instances. For example, for multi-threading in Wasm, each thread would most probably be an instance of the same module. Important to note that unlike in some other instruction sets, Wasm has no low-level system instructions for interrupts or peripherals access. Any communication with the outside world is done by explicit imports and exports declared on each Wasm module. This is a great security property since the strictest virtualization level is the default. Of course, everyone can define their own imports and exports for low-level system functionality. But then inevitably a question arises, how do you maintain a consistent and ideally stable API and ABI that modules can rely on? To answer that question, a standard for these system APIs is being developed called WebAssembly System Interface, abbreviated as WASI. It is specified as a collection of multiple modules for different system APIs, command line interfaces, sockets, clocks, and so on. The host app and the Wasm runtime have full control of the features exposed to modules via this interface. Circling back to security concerns, the Wasm runtime and the host app have full control over the APIs. If a module needs file system access, it's easy for a host app to provide a virtual file system. If a module tries to open a socket or even make an HTTP request, the host is free to deny that request or even provide some fake version of the internet. In certain cases, determinism is crucial, as it means a module always produces the same output for the same input. For example, build systems rely on determinism for incremental and reproducible builds. A build system extensible with plugins would have to make them deterministic to maintain these properties. A Wasm runtime can make everything deterministic, returning exactly the same timestamp for all clock-related syscalls, or same seed for random number generators. And there is no way for the module to distinguish those from the real values, which is the whole point of virtualization. A subset of WASI is also supported in WasmKit, the package I've demonstrated before, so you don't have to implement these syscalls manually in your host app. Remember this workflow I've shown you before? With latest Swift toolchain snapshots, you can compile embedded Swift to Wasm out of the box. And if you install a Swift SDK for WASI, a subset of core libraries, such as Foundation and XCTest, and a good amount of open source Swift packages become available too. Let's put what we've learned so far into practice using a more elaborate demo. We'll reuse existing Swift audio package from the Wasm examples repository, which I've presented at the Wasm I/O conference earlier this year. In this example code, we're building a web-based audio workstation. A new feature developed for this demo allows previewing and sharing synthesizer modules written in Swift and compiled to Wasm modules. We don't have to worry about modules doing anything malicious, since they run in isolation in a Wasm VM. The output of each module is combined on the server, and the result is sent to the browser for playback. The demo app is split into multiple packages: the guest package with Wasm modules and the host package with the Hummingbird server that runs plugins with WasmKit. Let's have a quick look at how this app works. When we load the index page for the first time, there are no modules available. Let's upload our first module. We can quickly listen to what we're working with after the upload is completed. Below the bass track, we can also see the mixed waveform. We'll try playing that. Important to note that these waveforms aren't pre-recorded. The sound is generated programmatically on the fly each time the module is running. That means the generated sound can be easily parameterized, and it can generate pretty much infinite amount of audio from these Wasm modules that are quite small, around 100 kilobytes each. We'll upload a few more track modules later. At the moment, you can see with a single track mixed, the mix is equivalent to that same track. But let's see how this mixed waveform at the bottom can be generated from multiple modules in the first place. For that, we'll start with the guest package written with embedded Swift. And support for embedded Swift is already available in any editor that works with SourceKit LSP. So I'll use NeoVim with its LSP integration to navigate through Swift code compiled for Wasm. Adjust the font size and switch to the core concepts of the Wasm modules. Here is the signal protocol, which provides which requires a single next function to be implemented, which infinitely produces samples of floating point type. The sample rate constant defines the number of samples we need to produce for 1 second of audio for that to be audible for us. Excuse me. Below that, you can see concrete implementation of this signal. A sawtooth-shaped waveform, which is a building block for a lot of interesting sounds. The source struct below that relies on a function that returns resulting samples. We rely on these signal types and a few more in the entry point for this plugin module. So let's open the main entry point for the base module here. Notice that expose Wasm attribute, which declares that the exported function can be called by the host in this final Wasm module under this given name. I will quickly summarize the rest of the code in the entry point function without a deep dive into signal processing. If you're interested, the whole plugin code base is a couple hundred lines of code that can produce a very basic musical sequence, which you've heard before. At the bottom of this entry point function, the audio buffer of 6 seconds long encodes the waveform that you've heard in the browser. The host for these modules is pretty much the Hummingbird template with the router function defined. For the index page, we discover previously uploaded modules stored on the file system. When modules are uploaded at the /wasm module URL, again, trying to understand if that's big enough. Right. We open a file handle and stream request body onto the file system, returning 200 OK status, HTTP status after that. Serving static files with Hummingbird and async sequence is easy and in a way mirrors the uploads code, the module uploading route, so I won't walk through it here. Now for the most interesting bit, loading Wasm modules and run it on the server to create a mix. Let's unfold that. In the mixed output initializer, for each Wasm module discovered on the file system, we parse it with WasmKit using the parse Wasm function declared in the WasmKit module. You can also see the mixed output conforms to the response generator protocol defined by Hummingbird. And the only requirement of the protocol is the response function implemented below. It takes a request and a context and produces a response. Notice the memory index variable here. As we are loading multiple modules, we need to keep track of the index of linear memory we're reading samples from. Here is a familiar initializer call you've seen before for the simple printer module. Here we provide a host module called audio with a function called encode. It takes 3 parameters, a context, which we ignore here, but it allows multiple modules to be rendered at the same time, the start address, and the byte count. Again, quite similar to the print function that printed hello world before. The crucial difference is that we look up the memory buffer by memory index over here, rebind it to the float type, and since all audio samples are floating point type, as defined by the signal protocol, we extend the samples buffer to make sure we don't overflow and try to write out of bounds, and accumulate these samples over here. We then return the empty result, similar to the print function in the previous demo. Each Wasm module is instantiated, and we call the entry point module function, which is main, and increment the memory index so that the correct instance of linear memory is read to populate the buffer. We initialize the request body and return the response with all of the results. Returning HTTP status to 100, of course. We walked through this much code, now we need a reward. We'd like to listen, of course, to more interesting mix here, so let's upload that. go back to the uploads page. Of course, just the bass line is very boring, so let's upload some drums, the hi-hat and the kick. So that's just the hi-hat and the kick over here. And the mix was just computed by the server. That's the output of the module. And again, to emphasize, this was all generated on the fly. There are no pre-recorded audio here. And the summary is that it allows you to extend your app with plugins that may be provided by the user. Back to slides. What have we learned today? Wasm is a great fit for lightweight virtualization when you need it for portability plugins and untrusted code execution. When working with Wasm, standardized access to file system, to system resources is a frequent requirement for which WASI is a standard solution. And lastly, multiple Wasm runtimes exist that can be embedded as a library, bringing these capabilities to your client and server apps. To wrap things up, I encourage you to try WebAssembly support in embedded Swift, which is now available in preview and Swift development snapshots, swift.org. And you can find the package I've just demoed at github/apple/Swift for Wasm examples. Also, check out WasmKit, hosted on the Swift Wasm organization at GitHub. And lastly, join the conversation at forums.swift.org. Thank you.